There are many different ways to describe a satellite's orbit about a planet. However, you are most likely to encounter one of two methods: Cartesian elements and Keplerian elements. The algorithms to convert between these representations are well documented, so we won't be covering them here. Instead, we'll go through a brief description of each set and the reasons why you want to use one form over another. Let's say you want to plot out the ballistic trajectory of a cannonball. You take out your trusty graph paper and draw two axes. The x-axis represents the downrange distance of the cannonball, while the y-axis represents its height. You'll probably place your cannon at point 0, and give the cannonball an initial velocity which has values in the x and y directions. Assuming that there is no air resistance, the only force acting on the cannonball is a constant downward acceleration of 9.81 meters per second squared. At any point in time, you can characterize the current state of the cannonball by recording the x and y components of its position and velocity. These state vectors, which are also called the ephemeris, are a simple form of Cartesian elements. In order to remember what the term Cartesian means, I prefer to think of the term cartography, which reminds me of maps, which then reminds me of grids. This is a little bit of a flub, since the Cartesian elements are actually named after the French philosopher and mathematician René Descartes. While it isn't exactly correct to use the term cartography in this sense, it's still a good way to remember what Cartesian means. When describing the Cartesian elements for a satellite, you will need to expand it out into 3 dimensions. The axes are typically placed at the center of the Earth, with the z-axis, the new dimension, pointing to the North Pole. In order to describe the Cartesian ephemeris for a satellite, you will need to know the x, y, and z position, as well as the x, y, and z velocity. Just like the cannonball example, you don't need to record the acceleration due to gravity. This can be calculated using the position of the satellite. The Keplerian elements are a completely different way of describing a satellite orbit. These are named after Johann Kepler and are also frequently called the classical orbital elements. The way that I remember what these elements are is to think that it's almost like sounding out the vowels in the alphabet: A, E, I, O, O, and nu. A is the semi-major axis. This describes the size of the orbit. For a circular orbit, the semi-major axis is the radius of the orbit. For an elliptical orbit, the semi-major axis is the average of the radius at perigee and the radius at apogee. E is the eccentricity of the orbit. An eccentricity of 0 is a circular orbit. An elliptical orbit has an eccentricity greater than 0 but less than 1. A parabolic orbit has an eccentricity equal to 1, while hyperbolic orbits all have eccentricities greater than 1. I is the inclination of the orbit. This parameter describes the tilt of the orbital plane. When a satellite orbits the Earth, its orbit is always balanced about the center of the Earth. It's not possible for the satellite to travel in a halo pattern as depicted here. Instead, if the orbit is tilted, it will spend a certain amount of time above and below the equatorial plane. When a satellite has 0 inclination, this means that the orbital plane is aligned with the equatorial plane. When a satellite has 90-degree inclination, this means that the orbital plane is perpendicular to the equatorial plane. This is also called a polar orbit, since the satellite travels directly over the north and south poles. O, or capital Omega, is the right ascension of the ascending node. For an inclined orbit, there are 2 points when the satellite crosses the equatorial plane. When the satellite crosses the plane and is moving upward, this is called the ascending node. When it crosses the plane and is moving downward, this is called the descending node. When you draw a line from the center of the Earth to the ascending node, this is called the line of nodes. The right ascension of the ascending node is the angle from the coordinate system x-axis to the line of nodes. This one may be a little confusing, so you may want to pause the video to study this picture some more. The next parameter, O, is little omega, not W. This one is called the argument of perigee. Remember that perigee means the point at which the satellite is closest to the Earth. The argument of perigee is the angle from the line of nodes to the satellite position vector at perigee. Again, you may want to pause the video to study this picture some more. The final parameter is nu, or the true anomaly. Since nu looks so much like v, which can be confused with the velocity of the vehicle, you will frequently see it written using another letter. I use the letter F. A top-down view of the orbit shows the true anomaly more clearly. The true anomaly is the angle from the position at perigee to the actual position of the vehicle at that moment in time. Okay, now that we've described Cartesian and Keplerian elements, in what situations would you use them? Here are the Cartesian and Keplerian ephemerides for a GPS satellite. They both represent the same instant in time. By looking at the first three Keplerian elements, you can get a pretty decent idea of what the orbit looks like. The radius of the Earth is 6,378 kilometers, so the semi-major axis is about 4 times the size of the Earth. By looking at the eccentricity, we can tell that the orbit is nearly circular, and we can see that the inclination is nearly 55 degrees. Using this information, we can draw the general shape of the orbit. In addition, you can add the argument of perigee and the true anomaly to get an approximate location of the satellite. As you can see here, it's very easy to get a good idea of the shape of the orbit from Keplerian elements. It's not quite so intuitive with the Cartesian elements. However, the Cartesian elements are very useful when propagating the orbit. By using small step sizes, you can use a numerical integrator to determine the new position and velocity of the satellite given the current position, velocity, and acceleration. With this method, you can also add in accelerations from other forces such as gravitational effects from the sun and moon and solar radiation pressure. Depending on the fidelity of your force models, you can get some very accurate simulations using this method. This is not quite so easily done when using Keplerian elements. Thanks for tuning into Orbit Nerd, where we make astrodynamics easier.